Okay, here we go with N35 and the spontaneity of redox reactions. And as you're going to see, and as you're going to start to, as we progress through this, and we start using the unit of measurement of volts, it's gonna, you're going to obviously start thinking about electricity and potential energy of electrons to move through a conductor and current and all that other stuff. And actually what happens is not only do you learn about spontaneity reactions, but you also start to think about how something like an electrochemical cell or a battery actually starts to produce direct current. Anyways, so the first thing that I want to do for this set of notes, obviously we're going to run through this. There's a couple of things that you have to have kind of in your head and at your fingertips before we even get going. So the very first thing I want to do is I want to make sure, pardon my cough, that we have a good understanding of what is meant by an oxidizing and a reducing agent. Um, when I was just doing balancing equations, we had this redox reaction where we had S2O8 negative 2 plus CH4, which is methane, going to CO2 plus H2S. And we went through that whole balancing equation stuff, and you ended up with a big long chemical equation. It ends up being balanced. But there's a couple of things that we have to get out here about the vocabulary. This chemical over here, the S2O8 chemical, and the CH4. So these are the two reactants. We're not talking about the products here. We're talking about the reactants. So these two reactants have very specific labeling to them that is just part of the redox vernacular. And so you have to learn what what the labeling is and what these words are, so that in conversation, when you hear me or you hear any other chemistry class that you're in, when you hear these terms, you're not confused by what that person is talking about. Okay, so there are two terms. One is oxidizing agent and one is reducing agent. And yes, they're going to be related to which one oxidizes and which one reduces. However, it's kind of confusing. The term agent, and I'm going to go up to the title actually. I'm going to highlight the title up there. The word agent actually means causes. So if you are an oxidizing agent, you cause oxidation. You don't oxidize yourself, you actually reduce yourself. And if you're a reducing agent, you cause reduction, which means you oxidize yourself. So it's weird because it's almost backwards terminology. You have to stop and you have to think about that the agent causes something to happen. So if I'm referring to these two reactants, I've got one of them is going to be the oxidizing agent and one of them is going to be the reducing agent. The oxidizing agent will be the one that contains the atom that reduces, and the reducing agent will obviously be the one that has the atom that is going to oxidize. So in order to do that, in order to establish which one oxidizes and which one reduces, you have to come up with oxidation numbers. And just like we started with in this unit, you compare the oxidation number of an atom before the reaction to an oxidation number of that same atom after the reaction. Once you've kind of established which one's the oxidizing agent or which one's the reducing agent, doesn't really matter, the other one is obviously going to be the other guy. So I'll give you an example. I'm going to choose the easiest one between the carbon before the reaction and the carbon after the reaction compared to the sulfur before and the sulfur after. Typically, like I said earlier, the oxygen and the hydrogen is not going to be involved in the actual reduction and oxidation. They're along for the ride. So I'm going to do the oxidation number for the carbon on the left-hand side and the right-hand side. So hydrogen gets priority in CH4, and the hydrogen's +1. There's 4 of them, that's +4. That means this carbon is going to be -4. over here on the left-hand side, or sorry, on the right-hand side, on the product side, the CO2. Oxygen has higher priority, and oxygen is -2 with a higher priority. That means the carbon is going to be +4. Okay, so the carbon atoms, okay, now granted, on the left-hand side they're attached to hydrogens, and on the right-hand side they're attached to oxygens. So they're attached to different things, but the carbon atom themselves have actually undergone from -4 to +4 is an oxidation, because the oxidation number went up. The only way you can go up is by losing electrons. That's how that thing went up. So as soon as I establish that the CH4 contained the carbon that oxidized, you now say, and I'll use my little highlighter thing here again, you now say that that molecule, so CH4, and I'll write it out as a sentence, CH4 is the, now because it oxidized, it is the reducing agent. The thing that oxidizes is the reducing agent. Which leaves us with the S2O8, therefore, must be the other one. So the S2O8 -2 is the oxidizing agent. If you wanted to prove that, we could do the oxidation numbers of the sulfur, and you would see the sulfur atoms reduced their oxidation number by picking up electrons, and therefore they would have reduced, and so they would have been the oxidizing agent. Now, quickly notice that I've used the whole molecule, the actual chemical you would put into the container to do this chemical reaction. You actually call the whole molecule the oxidizing or the reducing agent, okay, not just the individual atom. Okay, so that terminology is really key. That's first. The second thing, and everyone should have one out because this is like a critical piece of information, is your data booklet. And the very last page of your data booklet, so the last table you're going to see, is called the standard reduction potentials of half cells. So I've got one up here on the screen, and your photocopied version is actually kind of weak. It's kind of blurry. This PDF is way more clear. So you can see on the table, the printing's really small. So if you have not very good eyes, it's kind of hard to see. But this table is going to be out, and you're going to need this thing. So let's put it off on the side right now. You look at it, and it's got some almost very similar organization to the Ka table for the acids. We're talking about a different concept here, but the actual structure of it has a very similar principle to it. You've got the two big thick arrows on the left side and the right hand side. The one on the left hand side goes from weak to strong as you go from bottom to top, and then the one on the right hand side goes from weak to strong as you go from top to bottom, like the opposite strength concept that we had with the acids and its conjugate base on the Ka table. So we'll come back to that feature very quickly. The other thing you will notice on here, a couple of things you should always pay attention to, is there are numbers, the numerical values on here are in volts, and volts are a measurement of the energy of electrons. And we'll just leave it at that. We're not going to get too physicsy in here, but it gives you a sense of the potential for an electron to move from point A to point B. So, I mean, it's actually called an electromotive force, so the push for something for an electron to actually move. You've also got in the title actually states standard reduction potentials of half cells. So I want to walk through that entire thing. So the word standard. Standard means under a certain set of conditions. And the conditions are written in italics down there. So standard conditions mean 25 degrees Celsius and 1 molar concentrations. If we're talking different temperatures, we're talking different concentrations, then the numbers you see on this table in terms of the volts, they get altered ever so slightly. You get a slightly more concentrated solution and you're going to get higher potentials. If you get obviously lower than 1 molar, you get lower potentials. The temperature is higher temperature, you'll get a higher potential, and vice versa with the lower temperature. So those things are temperature and concentration dependent, those voltages. Later on at future university science courses, there's something called the Nernst equation that takes into account those concentrations and temperatures, and it's a little bit more of a formulaic thing. The other thing you're going to notice on there is it actually has titles on it: the oxidizing agent and reducing agent. So as we just talked about, oxidizing agents are on the left hand side and oxidizing agents reduce. On the right hand side you've got the reducing agents, which are those things that oxidize. So the table is set up in such a way that all of the reactions that are on this chart, okay, every single one from the top to the very, very bottom, has the thing on the left reducing to form the thing on the right. And you can kind of tell that because the electrons are on the left hand side, as a reduction half cell would be. But you also notice the arrows are two directional, and anything that can reduce, going left to right on this line, on any one of the lines, anything that goes reducing from the left side to the right hand side, well, that chemical produced on the right hand side can turn around and oxidize back into the thing that's on the left. So if you look at the very top line of this chart, and let's go with lime green. So if I look at that very top line of the chart, what that line is actually telling me is it's telling me, well, F2, so fluorine in its elemental form, can pick up 2 electrons, reduce to form 2 fluoride ions, 2 F minuses. And the potential to do that is plus 2.87 volts. And that's called its E value. And the little E with the little, like, it looks like a degree symbol, it's actually called naught, N-A-U-G-H-T. It's old English. Anyways, so E naught, the naught stands for standard. And so that standard potential for F2 to reduce to F minus is 2.87 volts. But if you look at that the exact same line and you go back the other way, F minus oxidizing back into F2 is the exact same line. You just look at it in the reverse direction. You go from the right over to the left. And if you reverse direction, it kind of stands to reason that you would reverse the sign of that value that's on the right hand side. So if it's positive 2.87 going from left to right, then it stands to reason that if you're going right to left, it's negative 2.87. And that's exactly what you're going to do on using this chart. Is we know that redox reactions are both a reduction and an oxidation combined into an overall reaction. Well, when you start thinking about spontaneity and electrons spontaneously going from chemical A to chemical B, it kind of depends on their desire to do so. And so those two halves are going to be put together. The desire for the electrons to do the reduction, to join something and form some product, and the desire of the electrons to leave the reducing agent and oxidize and form the products of the oxidation. And we're going to use this chart to combine those two halves and figure out whether something is going to be spontaneous or not. So this chart is going to be very, very critical. Just like the Ka table, you can kind of make some logical connections here that if something wants to reduce really, really easily, where is it here on the chart? Well, if it wants to reduce really, really easily, just like an acid really wanted to give up an H, it's higher on the table on the left-hand side. And so the thing that wants to reduce the most in the universe is F2. It's on the top of the chart on the left-hand side. It's the most skookum oxidizing agent that's out there in the universe. And it forms F minus really, really easily. But you can flip that coin and you can say, well, if you have F minus and you're trying to get it to oxidize to F2, well, the opposite tendency occurs. F2 reduces really easily. F minus would oxidize very poorly. So if we say that F2 is the strongest oxidizing agent in the universe, we would then be able to say F minus is the weakest reducing agent in the universe. Those two are opposite to each other. Now, as you kind of get a sense of this table, as you go down the left-hand side, you get weaker and weaker and weaker as an oxidizing agent. Like you start to see, as I kind of scroll down here on the chart, you get down to the very bottom of the chart. Okay, and I'll highlight this line down here on the bottom. Well, the worst thing on the chart for reducing is lithium plus 1. That's the weakest oxidizing agent. It hates to reduce. But then on the flip side of that coin, on the other side, solid lithium, elemental lithium, oxidizes the best in the universe. Right? So they're opposite to each other. And then you've got everything in between. So getting a sense of this chart is actually going to be really important. Now we're going to put numerical values with all of these processes and we're going to combine them. And because a reduction oxidation reaction is always two parts of the same, it's two parts to form an overall redox reaction. Well, on this chart we'll be able to take a numerical value for a reduction and a numerical value for an oxidation, combine them, and then draw some conclusions from that. Okay, so that chart's really important from that perspective, and you can kind of see when you're looking at the whole thing, you can kind of see that principle. One more thing about the table before we actually get into the notes and do some practicing here. This table is a relative table, and it's not the absolute potential of electrons to go from point A to point B. It is a relative scale, and it's all relative, and it's highlighted on your chart, but I'm going to highlight it even more. I'll put it, what'll I make it? I'll make it blue. This line right here, the line that has 0, well, the reduction potential of H plus ions to turn into hydrogen gas is not 0. That's not what it is. Electrons actually will go on to H plus, no problem. But this whole table, everything is built on the principle of relativity here. So everything is relative to that hydrogen line. It's actually called the standard hydrogen half cell. And so the standard hydrogen half cell is set at the 0, and then everything is then placed into its relative position. So if you in PE class, they line you up from shortest person to tallest person, and they say, okay, so the middle person, if everybody was relative to that middle person in terms of height, well, the people who are taller than that person would all be plus a certain number of centimeters or inches, and the people who are shorter than that person would all then be negative inches. That doesn't mean, Joe is minus 3 inches. That's not what it means. It means Joe is 3 inches shorter than so-and-so, that everybody's relative to. And so this scale is exactly the same thing. Everything's relative to that hydrogen half cell. Okay, now that table, have it at the ready, because I'm gonna be bouncing back and forth between the notes and that table because it's critical. That's where we're getting all our numbers from. Okay, so I now go to the notes, and we're gonna rifle through this, and I've hopefully kind of we've dipped into the table a little bit, and you know a little bit of the terminology, so we should be able to crank through this pretty quickly. Okay. Redox reactions occur when an atom from the reducing agent transfers electrons to an atom from the oxidizing agent. One oxidizes while the other reduces. Electron movement always has a potential to do so, and that potential energy is measured in volts. Therefore, every redox reaction written on paper can have its electrical potential measured in volts. You can calculate that value. Okay. I'm not going to worry about the joules per coulomb over there on the right hand side. I'll let the physics people get all nerdy about that. So number one, where do you find the data to do the calculation? That's the table we just looked at. It's called the standard reduction potential table. Last page of your data booklet. What does the potential mean? And this is really critical for the conclusions you're going to draw. And once you do a calculation of a potential of a redox reaction, if the final answer comes out to being a positive value, you have positive volts, that means that redox reaction is going to be spontaneous under standard conditions. If you do the math and it comes out to a negative value, that means that reaction under standard conditions is non-spontaneous. Now, notice I said standard conditions there, because if it's not standard conditions, again, you would be putting numbers into what's called the Nernst equation. You would still come up with whether it's spontaneous or not spontaneous, but it's a little bit more complicated then. So how do you go about doing the calculation? Like, how do we actually come up with that number that's positive or negative? And not only positive, negative, but then maybe also we're concerned about the magnitude of it as well. So if you end up with a cell potential that is plus 0.2 volts, well, is that as spontaneous as something that's plus 1.5 volts? And it's relative. So the plus 1.5 volt reaction will be much more spontaneous than the 0.2. And you would kind of expect the plus 1.51 would go like a bat out of hell, and it would be reacting really fast, and the 0.2 would just kind of be slowly dribbling along, reacting, yes, but barely reacting. Okay, so how do we do this? And you'll notice on every page of the notes I've written positive E cell is spontaneous. So how do you calculate an E cell? So that E just means cell potential, and the not means under standard conditions. There you go. So background. Number one, redox reactions consist of two halves, oxidation half cell and the reduction half cell. Cool. The E cell for any reaction will be the sum of the oxidation and the reduction half cells from the table. Number two, the data table lists reduction potentials for, you saw it, I mean, a huge variety of oxidizing agents relative to each other, which is relative to the hydrogen half cell originally. But then once they're all kind of put in order, then you can kind of tell relative to each other what they are. Not just relative to hydrogen, but relative to everything else that's on there as well. Okay, and so that understanding that concept on the data table, that things are relative to each other, really critical. Number three, every reduction half cell on the table is also an oxidation half cell, and that's what I was talking about. If you look at it in the reverse direction, so as you go from right to left on that table, you're actually thinking about the oxidation of that thing that's on the right. The arrow there for number three, so this is a pretty critical statement right here. Okay, so I'm gonna highlight it here and emphasize it. So the potential, the standard potential of the oxidation will be the same stated magnitude. So the numerical value on the chart will be exactly the same, but it will have the opposite sign. So if the reduction on the table has a negative 0.5 volt, that means the oxidation in the reverse direction on that same line would be positive 0.5 volts. Okay? So here's my example. On the table, the line Al plus 3 electrons goes to Al tells us two things. The reduction of Al plus 3 has a potential of negative 1.66, but the oxidation of aluminum, okay, so the reduction of the Al plus 3 versus the oxidation of the aluminum elemental, two different chemicals there, right? Different states of the same chemical, I guess. And same magnitude of potentials, but different signs. So what conclusion do you actually make from that? Well, the conclusion would be that Al plus 3 ions don't really like to reduce because it's a negative, pretty strongly negative potential, but elemental aluminum oxidizes quite easily with a positive, right? Okay, so here's how we do it. And the first one, I've filled in everything so you can kind of see how it works. So number one, the very first thing you have to do is you have to figure out what is your oxidation and what is your reduction. Okay, so hopefully we've done enough reactions so far in the balancing and also in N33 when we first introduced this stuff. You've started to look at a redox reaction as two parts, the reduction and the oxidation. These ones are oftentimes pretty easy to see as well. We don't get super complicated on these. So if the reaction was a solid piece of zinc is reacted with gaseous chlorine and it formed Zn plus 2 and 2 Cl minuses, which, let's face it, more than likely would have, this is not in water, so though the zinc plus 2 and the Cl minuses would have probably clumped together to form zinc chloride solid powder ionic compound. So the oxidation half cell would be the zinc. So the zinc is oxidizing to Zn plus 2 and the reduction is the Cl2 reducing to Cl minus. Again, oxidation numbers kind of tell you what partnership is doing what. So then what I do is I pull out the chart, right? And I've got the zinc and the chlorine. So I'll go quickly, just, I mean, you'll get the sense pretty darn quickly. But, so if I'm looking for the zinc line, so here's the zinc line down here. There's zinc right here. So that's the zinc line. So you'll notice that I say the word line. I don't say zinc plus 2 or I don't say Zn. I say the zinc line because when I say the zinc line, it actually is talking about two different chemicals. Zn plus 2 reducing or Zn oxidizing. And so you have to ask yourself the question, well, in this reaction, what is happening? What form of zinc is forming what form of zinc? Like you go through that process. And so in the question said, there it is right there, so it's Zn going to Zn plus 2, which means that you're actually thinking, and I'll put it in blue, you're actually going in that direction, right? So we're starting with the Zn and we're going to Zn plus 2. That number that's over there on the right hand side, that minus 0.76 is for the written as its reaction, or sorry, it's the reaction as it's written on the chart. So that's actually the potential for Zn plus 2 reducing to Zn. So we switch the sign. And so we actually have plus 0.76. And so you come back to here and you can see that there I've written it, and I've even written a little note to you that we switched the sign. Okay, cool. And then the chlorine, again, chlorine is Cl2 turning to Cl minus. We try and find Cl2 going to Cl minus. Now, there's so many chemicals on this chart that let me give you a sense of how you're going to kind of narrow your focus. And typically what happens, and this should match some of your logic, right, from what you've learned, I don't know, like you started learning it in Science 9, I think. Metals have a tendency to lose electrons and form positive ions, right? So metals like to oxidize. Elemental metals like to oxidize. Elemental nonmetals like to gain electrons and form negative ions. So if you're looking for an elemental thing, if it's a metal, you are probably going to find metals on the bottom right-hand side because they oxidize. So if I go kind of to the bottom of the chart here, let me get a little bit smaller so we can see more. Look at everything that's on the right-hand side at the bottom of that chart. They're all metals. And not only that, but you're actually getting the metals that tend to be really reactive ones, the alkalis, the alkali earths, so on and so on and so forth. But you tend to find metals that are over there. Now, as you start to go higher and higher, you start getting some kind of weird things that are on there. Not every metal is low on the right-hand side. There are some metals that are higher than others. And I'll point out a couple that are kind of, they're interesting, and I'll make them pink just so you can see them. Look at the silver line and look at the gold line. Both of those, so gold, like elemental gold and elemental silver, are both quite high on the right hand side. They don't like to oxidize, which gives us a little bit of insight as to why they are considered precious metals. They don't oxidize very well. Gold is terrible, right? So you want something to stay shiny and, look like it's brand new and expensive. Well, if it's gold, it's not going to oxidize. You make something out of iron. Well, iron's way down here on the chart, right? So iron's way down here. And so iron's, it oxidizes quite easily. And so why would you make anything out of iron? It's going to oxidize all the time and look crappy. So if you're looking for elemental metals, you're probably looking on the bottom right hand side. On the other side of that coin, if you're looking for elemental nonmetals, you're probably looking up here on the top left hand side. And so you'll see there's F2, there's chlorine, there's bromine, where's oxygen? Oxygen in neutral conditions is right there. Oxygen in acidic conditions is right there. Iodine is not quite as good as the other ones, but there they are right there. So again, like, where are we talking? Right there, top half anyways, on the top left hand side, because elemental metals do have a tendency to reduce. Okay, so if I'm looking for chlorine, I'm probably looking in the top left somewhere, and sure enough, it's right there. There's my line. So back to the notes, and there's my chlorine line, and that's the number that was taken off the chart. So then what we do is we balance electrons as we typically would. So they're already balanced, 2 and 2, so they're going to cancel. And so the electrons would cancel, and so you end up with your overall equation, and you simply add the E cells. Okay, and you add the two together, so 0.76 and 1.36 is 2.12. Because that comes out positive, it's spontaneous. And not only that, but it's quite a, and you'll see kind of as you start doing some of these things, you'll see positive 2.12 volts is actually quite a high cell potential. That means that reaction is very spontaneous. Like, it'll react like almost catch on fire, kind of spontaneous type of thing. Like your typical battery is producing 1.5 volts. And then if you've got a 3 volt or a 9 volt battery, it's because they're in series, not because the reaction's producing more than that. So a 2.12 volt chemical reaction is actually quite a significant little reaction that might actually be fiery, as it were. Okay. Now, what happens if we start taking some stuff away? So at this point, I'll do one, and then I'm going to basically, if we go through this whole thing, then there's a whole bunch of questions that you can answer kind of on your own and together, and we'll just put up an answer key in class. But I'll go through this one real quick, so right, and I don't need to explain a whole bunch of things anymore because now we've got it. So I've got Mn plus 2 reducing into Mn, and I've got, I'll use a different color, and I've got H2O2 turning into O2. Now if the Mn's reducing, then this thing must be oxidizing. So right off the bat, I mean, you can see down below I've separated them to the oxidation and reduction. Where am I looking for these chemicals? Where would I look for H2O2 on the chart? Where would I look for Mn plus 2 on the chart? The thing that is reducing, so in this case it's the Mn plus 2, I'm going to look for it on the left-hand side of the chart. So let's go to the chart. Let's look at the left-hand side. Let me get rid of all the... I think if I erase it, it erases the whole chart too. Oh no, it doesn't. Cool. Cool, cool, cool. Cool, 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 cool. Okay, so Mn plus 2. But it's reducing, so I'm going to look for Mn plus 2 on the left-hand side. And because it's a metal line, because manganese is a metal, probably going to be in the bottom half of the chart. So I'm looking. Here it is. Found it. There's Mn plus 2. Mn plus 2 reducing into Mn has a cell potential of negative 1.19. So I go back to here and I go, this guy reducing is negative 1.19 volts. Cool. The H2O2 reducing, oh boy, and it does say it's in acidic solution, so I might be looking at a fairly complicated line over here on my chart. So I go over here and I'm thinking H2O2, it may have some H pluses on either side, I don't know, maybe left side, maybe right hand side, I don't know, but I'm looking for H2O2 on the left hand side. So start at the bottom. That's water down there at the bottom. I go, and you actually end up finding it really quite high, as a matter of fact. Here's the H2O2 line right up here. So there's H2O2. It's in acidic solution because it's got H pluses in it. So this reaction needed to occur in an environment that had acid in it as well. And if you've got that scenario, then that has a potential of positive 1.78. Positive 1.78. So this guy is positive 1.78 volts. Now, like if you're going to actually balance this equation, right? I mean, you should be able to have them in separate things. But, hold on, I may have grabbed the wrong one. Oh, I did. Did you notice the product? So, whoops, that's not what I want. So if you look at the product, my product was O2. I need a line that has H2O2 going to O2. The one that I chose up there was going to H2O. I wonder if there's another line on here that has H2O2. And I can't find it. Anybody? I think maybe I wrote the equation wrong. Shoot. Okay, I'm gonna go back and I'm gonna change the notes. Let's change the note. Let's change the notes. So let's go with this guy. We're gonna change it to I'm gonna change it to H2O because I didn't think actually. Reduction. That guy's in oxidation. No, because that should have been a reduction as well. Hold on a minute. Oh, I know why. Oh, hang on a minute. Have you spotted my mistake? And I'm going to claim that I did this on purpose. The H2O2 is oxidizing to O2. What side of the chart was I looking at? I made the critical mistake. I had the H2O2 on the left-hand side going to the right-hand side, which is the reduction of H2O2. That is wrong. That chemical reaction had H2O2 oxidizing into O2. So I should be looking for H2O2 down the right-hand side. So if I'm looking for H2O2 down the right-hand side, there's H2O, 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 H2O. Here it is. There's your H2O2 on the right-hand side, oxidizing to O2. And it produced 2 H pluses and 2 electrons. Okay, so I'm just going to finish the reaction. So I'm going to come here, and it's plus 2 H pluses plus 2 electrons, and this is 2 electrons there. And the potential was, here's the potential if we're going left to right, but we're not, we're going right to left. So that is going to be negative 0.70. Negative 0.70. So what's the overall reaction and what's its E cell? So the electrons cancel. Nothing else cancels, so you're going to have H2 plus H2O2 plus Mn plus 2 going to O2 plus Mn plus 2 H pluses with an overall E cell of negative 1.89 volts. Add them together. The conclusion, because it's negative, is that this guy is going to be non-spontaneous. Okay. Now this last one, I want to show you. I want to do this one as well with you, simply because it's got a concept that I want to make sure that I address and I emphasize. So on this one, the calcium plus 2 plus K is going to K plus 1 and calcium. This is a net ionic equation, so I've eliminated spectators. There would be some negative ions in there somewhere. I mean, who knows? There might be some Cl minus or something to balance the charge in the reality of the chemistry. But the oxidation half cell would be, I'll use blue. The oxidation half cell would have been the K going to K plus 1 electron, and the calcium plus 2 electrons going to Ca. Okay, now before I do any of the numbers, if I was going to balance this equation, because pardon me, if I was going to balance this equation, this I would have to multiply the top one by 2, because there's 1 electron being produced, and that needs to cancel the 2 electrons of the reduction. But this demonstrates a little bit of a point. So if I multiply the top one by 2 to make it balanced, so I go the top one times 2, and then if I write the overall reaction, then the electrons cancel, and you end up with Ca plus 2 Ks goes to 2 K pluses plus calcium. Now, hang on to the thought that the potassium one's multiplied by 2. So I have the calcium being reduced and the potassium being oxidized. So calcium being reduced, I go to my data table and I look for calcium being reduced. So calcium being reduced. Calcium's a metal, probably on the lower on the table. So I look and I look and I look, and it's really low on the table. It is, let me erase this one because I don't want to confuse people. So calcium line is right there. So calcium plus 2 reducing is as it's written, which would be negative 2.87. Negative 2. Whoops, oh, wrong one. Negative 2.87. Calcium reducing is negative 2.87 volts. Not very good. Calcium really doesn't want to reduce, right? You can kind of base that on 1, it's negative, and 2, it's quite a large number in the negative direction. But then I've got potassium oxidizing. So I need to find K on the right hand side of my data booklet, and here it is. There's the potassium line, but I'm going in from here to the left. Okay, and I'm going to leave that guy circled here, which means that the potassium actually really wants to oxidize. So I switch the sign of that, so it's positive 2.93. Positive 2.93. Positive 2.93. Now, we multiplied that equation to balance the electrons. We multiplied it by 2. So I wonder if we should be multiplying that E cell by 2, that 2.93. Should we multiply that by 2? Short answer, no. You don't multiply it by 2. The slightly longer answer is voltage is the potential of a certain number of electrons. And the potential for an electron to move from point A to point B doesn't matter how many electrons are moving, because the individual electron it's almost like it's feeling a force pushing it from point A to point B. And so therefore the actual overall potential doesn't change, because per electron it's kind of feeling the same force. And so we don't ever multiply any of the potentials by the coefficients we're using when we're balancing equations. So I'm just going to leave it as it is. So then we've already done the balanced overall equation, so then we add those two together. Now it's not a big number. Like, we're not talking about it being, bubbling and fizzing and going like a bat out of hell. But what we do note here is that it's still positive under standard conditions. And the calcium really didn't want to reduce. But what was really critical is that the potassium, its desire to oxidize, kind of outweighed the reluctance of the calcium plus 2 to reduce. And so the calcium plus 2 got forced to reduce because the potassium was stronger. And that's what happens with these redox reactions, is sometimes you can have a process, you can have a chemical that doesn't really want to do what the equation's saying it's doing, but it's being forced to by a more powerful half reaction. In this case, potassium oxidizing kind of forces the calcium to reduce. And it's kind of an interesting concept, because then you can start thinking about out there in the universe, some chemicals don't like to react, and yet they're forced to by other kind of powerful, more dominant chemicals. I'm going to come back to the table for a sec, because I want to show you this arrangement. It's something, and maybe you've already seen it. You've already kind of, in your own mind's eye, you've already figured this out. But if I were to circle in that last question, if I were to circle the last two chemicals that we threw together. We threw calcium plus 2 and potassium. It wasn't strongly spontaneous, but it ended up being spontaneous. If you put a circle around the two chemicals, the thing that reduced and the thing that oxidized, and you draw a line between the two of them, you have this very consistent angle or slope of the line that you get between those two things. And you can kind of take your pencil and put it on top of your reduction table. And if the chemical that's doing the reducing, the oxidizing agent, the chemical that's reducing, if you connect it with one end of your pencil to the chemical that's oxidizing, the other end of your pencil, and if that slope is the same slope as I've got here on the chart with that kind of slopes, high on the left and low on the right, it's going to be spontaneous. How steep that slope is how spontaneous it will be. If I take the previous one, we found out that the previous one was non-spontaneous, and we were reducing Mn plus 2, so I'll circle those guys as well. So Mn plus 2, there's Mn plus 2 right there, and we mixed it with that H2O2 dude, this one up here. Make it smaller so I can get both of them on the screen. Now, if I draw a line between those two, or you put your pencil over top of those two, they form the opposite slope. And anytime if the thing reducing is above and to the right of the thing reducing is below and to the left of the thing oxidizing, it's going to be non-spontaneous. And if the thing reducing is above and to the left, it is going to be spontaneous. And so you can actually, if I just ask you a real quick question about, is this going to be a spontaneous reaction? You don't even need to calculate a number, really. If you know where the two chemicals are on the table, you can just kind of connect the two dots and say spontaneous, non-spontaneous. You can work that quickly. Okay? Back to the notes here for a sec. So, now what I want you to do, and actually I ended up going all the way through all of these things, is I want you to, on page 5 and on page 6, there's a whole bunch of questions that I want you to do, and then there's going to be some practice for you guys to do as well. Okay, but that's it for the lecture portion here. If you have any questions, you know where to find me on Teams, and we will talk soon. See you later.